On this lesson, we will talk about eliminating parameters in a parametric equation. So let's get started. So now what we have been discussing so far is that here we have a set of parametric equations, one equation for y and one equation for x. So here we have the x is represented by t squared minus 4 and y represented by 1/2 of t. And now the idea is for us to come up with the single equation that will still represent the same path that these parametric functions follow, but without the parameter t. So we want to get rid of t, but we still want to come up with an equation that will represent the same path that these two functions, or those parametric functions follow. So how can we get rid of the parameter? Well, we're going to start by just rewriting our function. So instead of writing x of t, I'm just going to write it as just x, because remember that this expression just gives you the x coordinate, and my parameter for y. So notice that all we have done is we just took our parametric equation, one for x, one for y, and now we just made it into more simple expression. Now that we have done this, the objective now is notice that you have two equations, and they both have a parameter of t. So now you want to choose one of these two equations to solve for t. But I can see that solving for t for y, it makes the most sense because it's just straightforward. Because if I do multiply by 2 on both sides, now I know that t is equivalent to 2y. And by doing this, now we have an expression for t. So t is equivalent to 2y. But notice that I also have an equation from my x portion of the parametric equation, which is in terms of t. So now I can go back to the second function and substitute t for 2y, and let's see what happens. Now we have this expression, but now notice that we have a simple expression with no parameters. There's only two variables, x and y. So now we can think about it just a Cartesian equation. So let's just write it in standard form. So let's distribute that. So now this becomes 4y squared minus 4. Let me just solve for y, so I can write it down in standard form. So to solve for y, I need to add 4. And now this becomes x plus 4 equivalent to 4y squared. Let me divide it by 4. Now we have y squared equals x plus 4 over 4. And by taking the square root, now notice that I have properly solved for y. So now I know that y is equivalent to plus or minus the square root of x plus 4 over 4. So now notice that we have an equation. Let me just write it here more clearly. So the equation that we have come up with is y equals plus or minus x plus 4 over 4. So what we're saying is the following. This equation that we just found out should have the same path as the parametric equations had initially. But now the benefit is that in here, we don't have the parameter. Here is just a single equation that represents the actual path of the curve, where in this case, the path was cut into two different equations, one for x and one for y. Well, let's actually make sure that we're talking about the same function. So here, notice that in our example 1, here we have our parametric equation. Here we have our parametric equation. This is the parametric equation that was given to us initially. Notice that it's for x is t squared minus 4, and for y is 1/2. That's exactly what we do have here. And notice that now it seems that the orientation is following this way. Now you just wait for a second. Notice that this seems to be the orientation. But now let's graph our results, because we're saying that if I graph the equation plus minus square root of x plus 4 over 4, it should have the same curve. Well, let's see if that is true. So that's the plus, and that's the minus. And now notice that this equation that we just came up with has the same curve as the one that was given to us by the parametric equation. That's the parametric equation. So now, even if I delete the parametric equation and I just plot the equations that we got by eliminating the parameter, notice that we still have the same curvature, we still have the same path as it was given to us initially from the parametric equations. So that's how we can eliminate the parameter. If you follow these 3 steps, solve for t, plug it in, and write it down in standard form, then by doing that, you have come up with an equation that still follows the same path, but the benefit of it is that there is no parameter on it. Let's do a couple more examples now. Let's take a look at example 1. Let me just move this a little bit downer. So here, let's try to eliminate the parameter. Here, let's try to eliminate the parameter. And again, we got 2 parameter equations. So now we choose. Which of these two is easier for us to solve for t? I mean, I can kind of see that for the equation that represents the x value, it's easier to solve for t because there's only one t. So I'm just going to get my equation. Let me actually do this in red just to be consistent. I'm sorry, let me actually do this in black to be consistent. So here we have that x is equivalent to 1 over t plus 1. And I want to reinforce this. We could solve for t in the equation given to us by y, but I just don't want to do that because now there's double t's right here. So that might become a little more complicated. But let's just solve for t under the x equation. And in order for us to solve for t, I can just raise the second exponent to both expressions. So now by doing that, I have that x squared is equivalent to 1 to the second, it's just 1, and the square root to the second, it will cancel out. So now you ever have t plus 1, and we can definitely solve for t now, because if we cross multiply, we're going to have the result of x squared times t plus 1, and that's equivalent to 1 times 1. And notice that what I'm doing here, I'm cross multiplying. So now we have the equation that tx squared plus x squared is equals to 1. And again, we're solving for t. So let me get rid of this x squared. So now I have that tx squared is equivalent to 1 minus x squared divided by x squared. And notice that by doing this, the x squared cancels out. So now I have an expression for t, where t now will have the expression of 1 over x squared minus 1. Now 1 over x squared is 1 over x squared over x squared, that's 1. So now notice that what we have done so far is we have come up with an expression for t. And this is exactly what we needed to do. So now that I know an expression for t, what we're going to do now is notice that t, we got it by manipulating the expression for x. So now we're going to get this t and we're going to plug it into the equation for y. So now we're going to have that y is equal to 1 over x squared minus 1. So I just plug in this t value to the numerator. And now we still got to solve it. We still got to plug it into this t. So now we got 1 over x squared minus 1 plus 1. Notice that at this point, we do have an equation for y in terms of x, but this definitely doesn't look nice. So let's just try to simplify our expression. So now notice that the numerator can be just written out as 1 minus x squared over x squared. And note that the denominator can be written as 1 minus x squared plus x squared all over x squared. So now that we have it in this form, let's try to simplify this. Notice that here the x squares will cancel out. And now we're going to have the following. So now we know that y is equivalent to 1 over x squared all over 1 over x squared. And remember that if you're divided by a fraction, this is equivalent to just multiplying by the reciprocal. And now this way, the x squares will cancel out. And now we have an expression for y, 1 minus x squared. So what we're saying so far is that this equation that we have just gotten here should have the same path as the parametric equations that we were just given. So if I were to graph 1 minus x squared, that should be the same path as if I were to just graph it the parametric equations. Well, let's see if that is true. Let's take a look at our, so that's still, example 1 is still running. So let me just close that in here. Notice that this is example 2. Here we have our parametric equation. For x is 1 over the square root of t plus 1, and for y is t over t plus 1. Notice that here we have our direction, or our location. Let me try to slow this down. Notice that the location is just pretty much just going towards the origin. Now what we're saying is, if we were to just graph the function 1 over x squared, which I'm about to do right now, it should have the same path. So notice that it does have the same curvature. All we got to do is just limit our domain for my new function. But notice that at least when it comes to the actual parameter, we do have here my parametric equation. This is my parametric equation. But if I graph our result on top of it, notice that it's essentially the same graph. Even the point of location should still follow this. The only condition is that now we just got to restrict our condition. We just got to restrict our x value, which it seems that at least we only want those x values that are greater than 0.2. So let me just go back to my function here. So even though this is the original function, we still got to put a little parameter, and we got to say that the x values should be greater than 0.2. So now this is completely true. So now we have a function with no parameters that still represents the parametric equation. Notice that's essentially the same function. Here we have the parametric, and if we graph our results, notice that we do have the same function, the same path, the same curve. So there's one more example that I do want to discuss. And this example deals with sine and cosine functions, because at least when it comes to sine functions and cosine functions, there's a little trick that we do have to discuss. And again, the objective here is just to get rid of the parameter t. So let's get rid of the parameter t, but notice that if we follow the same path, or if we follow the same direction as we were just doing a couple seconds ago, we could write x to be sine of t, and we could write y to be 3 cosine of t. So we first get rid of this parenthesis t. But now the question is, how do I get rid of t? Because that's still the main objective. We want to get rid of t. Well, for that, when we're dealing with the sine and cosine function, we're going to solve for the function in terms of t. So in order to solve for the function in terms of t, I'm going to divide 3 to both sides. And now notice I have x plus 3 is equivalent to sine of t. And also for y, I have cosine of t. So let me solve for cosine of 3. So now that cancels out. And we have y over 3 is equivalent to cosine of t. And now that we have it in this form, notice that there's a relationship between sine and cosine. Recall that from trig, we have this relationship, sine squared plus cosine squared is equivalent to 1. So therefore, I can substitute the sine to put it here. So now the relationship between these two functions is that x to the third square, because that is my sine, so I can just substitute with the sine, plus my cosine square, which notice that cosine is y over 3, that is equivalent to 1. And now notice that thanks to this relationship that we do have here, if we plug in our sine function and we plug in our cosine function, now we have an equation with no parameters. There is no t going on in here. So now notice what we do have. So now we have x squared over 9 plus y squared over 9 is equivalent to 1, which is equivalent to x squared plus y squared all over 9, equivalent to 1. And if we multiply 9 to both sides, notice that we have x squared plus y squared is equals to 9. And you might recognize this form because this is definitely the form of a circle. This is going to be a circle So this is going to be a circle with the radius of 3 and also its center at the origin. Well, let's see if that is true. Let's graph our parametric equation. Let's graph our parametric equation, and then let's graph our result and see if they actually match. So going back to our decimal activity here. So here we have our, this is going to be our parametric equation. Should be a circle, here's a big circle. So let me just run it through. Notice that this is our parametric equation, and it seems like our direction is following this way. So this is our parametric equation. Now let's graph our result. They match. X squared plus y squared equals to 9. Now we have an equation with no parameters. There is no t in this equation that can still follow the same path that the original parametric equation was following. And one thing that you might notice is that now we were able to represent a circle in terms of parametric equations. And you will see later on that we can also represent all those conic sections that we discussed at the beginning of the year using parametric equations. Parabolas, ellipses, hyperbolas, they can be described using parametric equations. But this is just a small lesson where I wanted to just share some extra examples when it comes to eliminating the parameter in a parametric equation.